Well, hey there, it's Dr. Franklin, Assistant Professor in the Department of Psychology at Norfolk State University, and I am back to talk about z-scores. A z-score is a standard score, and whenever we standardize scores, we are essentially taking a numerical value and transforming it in such a way that will cause the mean of that set of values to be 0 and the standard deviation equivalent to 1. When we standardize scores, we're able to determine if outliers exist in the data set, and we're able to make cross comparisons of samples. So I want to talk about standardization as it relates to the normal curve. The normal curve, or the bell-shaped curve, is a curve that would result if your data were normally distributed. A normal distribution is symmetrical, and there's 50% of the data to the right of the mean or higher than the mean, and 50% of the data to the left of the mean or lower than the mean. And again, this is a curve that would normally result if your data was normally distributed. In other words, there wasn't any negative skews, positive skews, there was no bimodal distribution, wasn't a great deal of leptokurtic characterization or platykurtic characterization. Now, in a normal distribution, the mean, median, and mode would be in the center, and the standard deviation of the mean would be the equivalent of 0. And we'll talk about why that is in just a little bit when we actually work through some of the z-score problems. In a normal distribution, you also have inflection points, and each inflection point represents one standard deviation. So on the right of the distribution, you have positive standard deviations going left to right from the center. You see increases occurring, and then on the left, you have inflection points as well, and these will result in negative standard deviations. So from the center going right to left, you see a decrease of standard deviation units occurring. So standardization involves transforming a mean for a particular sample into 0 and transforming each standard deviation unit into 1. Now, once we calculate z-scores, we can apply it to this normal curve that you're looking at and be able to visually see how a particular raw score falls above the mean and how it may also fall below the mean. In coming lectures, we'll discuss the proportion of a sample you should expect to be between the mean and one standard deviation, and between standard deviation units across this normal curve. You will find that these percentages will be fixed as long as the distribution is normal. Now, let's talk about the formulas for a z-score. So for a z-score, we have two different formulas. We have the one that is utilized for a sample, which is a raw score minus the sample mean over a sample standard deviation. And we have a raw score minus a population mean over a population standard deviation. So what is happening in this formula? Well, in the numerator, we have a deviation for each formula. And then in the denominator, we have standard deviations. So essentially what we're doing, folks, is transforming our deviation, or transforming the raw score distance that a particular raw score is from the mean, into a standard deviation unit. We're standardizing that deviation score so that we can apply it to the normal curve, so that we can make cross comparisons, so that we can ultimately figure out if outliers exist within our data. So let's say we had a series of raw scores. Let's say we had x equals 44, had x equals 38, and we had x equals 48. And let's say we were given a population mean of 40 and a population standard deviation of 8. We can take each of these raw scores and standardize them by way of utilizing our z-score formula. In this particular case, we will utilize the z-score formula for a population. In actuality, folks, you could make an error and go with the sample formula, and as long as you identify the correct mean and the correct standard deviation, you'll still end up with the right answer. But for all intents and purposes, make sure that you understand what these Greek symbols mean so that you'll be moving forward with greater understanding of what you're doing and accuracy, because there are times moving forward where you will have to make sure you select the correct formula that is appropriate for the sample or population that you're working with. So let's calculate a z-score for 44. We got z equals 44, that's the raw score, minus the population mean, which is 40, over the population standard deviation of 8. When we do 44 minus 40, we end up with 4 in the numerator and 8 in the denominator. When we divide 4 by 8, we end up with a positive 0.50. Now, what exactly does that positive 0.50 mean? Well, in order to interpret this, we need two pieces of information. We need to know what the signage means, and we need to know what the numerical value represents as it pertains to the z-score. The signage tells us if the score is above the mean or below the mean. Now, if we have a positive sign, that means that it's above, and if we have a negative sign, that means that it's below the mean. We ended up with a positive z-score, which means that this particular raw score is above the mean. We can double check this by just coming back to our numerator, and we can see that 44 is higher than 40, so it makes sense that we ended up with a positive z-score. Now, the numeric tells us the distance in standard deviation units that a raw score is from the mean. So going back to our example, 44 is 0.50 standard deviation units away from the population mean of 40. Now, 0.50 standard deviations as it relates to this sample is 4. Why is it 4? It's 4 because the population standard deviation is 8. So if my z is 0.50 or half of a standard deviation unit and my population standard deviation is 8, then it makes sense that the raw score would be 4 points away. You can double check that again by coming over here and looking at your deviation formula, and you will see that the raw score is indeed just 4 points away from the population mean. Now, we can take this z of positive 0.50, apply it to this normal curve to get a visual representation of what we've just interpreted utilizing information in regard to signage and numerical interpretation. So 0.50 would fall likely right there, kind of treating this like a number line of sorts, okay, because these standard deviation formulas, standard deviations represent z-scores. And now we have a nice visual representation of 44 and its relation to the mean, which is 0. Now, some of you guys may be wondering, why is 0 in the center? Well, these z-scores represent standard deviation units. What do you think would happen if you tried to calculate a z-score for a mean? Well, let's do that real quick. So let's say we were calculating a z-score for a mean. Let's say we were doing 40 minus 40. We were curious to see how far the mean is from the mean, and we were going to divide that deviation by 8. We're going to end up with 0 in the numerator 8 in the denominator, and since we have nothing to divide, we're going to end up with 0. So it makes sense for the population mean and standard deviation units, the standardized score, to be 0, because when you try to do a z-score out for it, it's going to be 0. In other words, the mean isn't far from the mean because it is the mean, right? So keep that in mind as you move forward and as you draw up your own normal curves and create your own visual depictions.